Okay, so we are continuing with Wiener filtering discussions. So previously, we have discussed, let me write it like this, FIR Wiener filtering. So what do I mean by FIR Wiener filtering? So there is an estimator. This estimator is simply a linear combiner of last p samples of a process. Okay? So this is like a convolution type of relationship. It's a linear combiner. So the goal is estimation of this process dn with this estimator d hat of n. So the goal is minimizing the MSE, as we have said. dn minus d hat of n, second power. So I would like to minimize this. Over what? Over this w, let me say vector. Okay? So I define a w vector, last time we have discussed this, and x vector, input vector, and so on. I would like to minimize this, let's say, cost function according with respect to this w vector. So the result is, we have solved many examples of this equation system. So optimal W, minimizer of this, satisfies this, what we call the normal equation system. So this is the autocorrelation matrix of this x vector, and this is, let me write it a little better, cross correlation of the desired sequence or desired process and the elements of this x vector observations. Okay, so if I can, express this Rx and Rdx vectors, I am done. Okay, so today we are continuing with the same discussion. So we are starting IIR, infinite impulse response differently, Wiener filtering. So what do I mean by this? It is exactly the same setup. d hat of n is equal to, let me write it like this, let's say k prime minus infinity to infinity, h of k prime, x of n minus k prime. Okay? So it's almost like the same. I'm calling this right now h of k prime, or h of k. Okay? Then the only difference is, you may say, the indexes of the summation, the upper and the lower limit of the summation. Okay? So this is indeed an infinite impulse response filter. So if you check this impulse response h of n, now this is an infinite impulse response. This is just a sketch, obviously. So this is with respect to n. So this is an infinite impulse response filter. Previously we had a FIR filter. So the goal is, again, I would like to minimize with respect to all of these weights, okay, for k minus infinity to infinity, d of n minus d hat of n, parentheses square. Okay, that is it. So this is the IIR version of the earlier one. So what do we do? So let me write the following. If I take the partial derivative of this cost function, let's say, let me call this my cost function, j of, let's say, h vector. Okay. So what is h vector over here? H vector starts from h of, let's say, minus infinity. There is h0. It goes up to h of infinity. Okay? So it's an infinite length vector. So in this vector, there is one of these indexes k. So I am taking the derivative of this cost function. This is a partial derivative, as you see, with respect to, so this function of many variables with respect to h of k. So what do I do? Again, this is what we call the error at the nth time instant. This is error square. Then this is nothing but, if you do this, This is error square. There is 2 times E of n times. Now derivative of this with respect to kth variable. Okay. So we have done this many times. So this is x n minus k. Because h of k is multiplying x n minus k. And because of this differentiation, there is a minus sign involved. Let me put this minus over here. This is equal to 0, optimality condition. And again, no surprises. This is the orthogonality condition, isn't it? So if I write this one more time over here, so E of n, the error of the optimal estimator should be orthogonal to the observation x n minus k in this one of these observations, x n minus k, but this should be valid for all k's, because at the end I'll be taking derivatives for all possible k values. Okay, so one more time, this is the orthogonality condition. Okay, now if I go forward, now what should I do? If I express this E of ns over here, d of n minus d head of n, what do I get? Now I have d of n times this. So this is r dx of k. If I multiply d of n by x n minus k, take the expected value, I get that. Minus, but let me put this minus negative term on the other side of this equation, on the right hand side. So I have d head of n, this thing, times xn minus k. So this multiplied by xn minus k. So I get this. So xn minus k times this. If I take the expected value, Rx k minus k prime. Okay, so this equation, orthogonality, is also equal to this one for all k. Only thing that I have done is substitution of definition of E. Well, what do we see? Well, indeed, this is not different from this equation. Okay. For example, if you limit this summation, the indexes of this summation, or the orthogonality condition to these samples, what do I mean by that? To x of n minus 1, up to x of n minus p minus 1. Okay? Last p samples, including x of n. Then you have this FIR result. If I change this only this, then summations upper and lower limit. So you see that this equation, they're identical. In other words, this is matrix relation is nothing but this is p by p, p by n. P equations like that. Okay? That is it. So how am I going to solve this? That is the issue. So note that I have, this is, let me write with the other color, infinitely many equations with, let's say, infinitely many unknowns. Okay? Use this one. Unknowns. So what can I do about this? Well, if you have some experience in signal processing, then immediately you would do the following. You would say that, why not take DTFT of this? Why? Well, we have defined this DTFT as S dx e to the j omega. But let me write this with blue. If I take this DTFT, okay, S dx of e to the j omega. So about this one, this is h of j omega times sx e to the j omega. Okay? So why do I have such a result? Well, this is nothing but the convolution, isn't it? So I have an unknown filter, h of n, convolved with Rx of k. This is known, this is unknown. Of course, this contains infinitely many samples. So if I take its Fourier transform, discrete time Fourier transform, I get this one. Okay? So now this is equivalent to this. So can I solve for hj omega from here? Now it becomes a trivial operation. So from here I get h e to the j omega as s dx e to the j omega sx e to the j omega. So from here, can I go back and find h of n? Well, that's what we call inverse DTFT, isn't it? If I calculate this inverse DTFT, I am done. So again, we see, the use of transform domain calculations. So this infinitely many equations turn into a pointwise equation for every frequency, as you see. So I have something like that. So let me say, well, this is, let me write it like this. This is IIR, optimal filter, infinite impulse response. But let me write NC, just to mention that this is IIR non-causal. IIR non-causal filters, optimal filters, frequency response. Okay. So what do I say why do I say non-causal? Because this has lags at every sample, including positive indexes and negative indexes. So is this the end of the problem? It's almost like the end. Okay. But let me also find the minimum error achieved. The achieved value with this filter, let's say HIIR non-causal e to the j omega. Okay, but let me maybe before this I should mention what's the meaning of this. Of course you know the meaning, but this is nothing but the power spectral density, isn't it? This has a special, not only a transform relation, this is the power spectral density of xn process input process. So this is the cross power spectral density. Okay, that is it. So this has a physical significance also, especially. We have discussed this in length in earlier lectures. Now let me try to calculate this achieved MMSE value. Again, how can I do this? Well, this is E of n square with h of n is equal to HIIR non-causal of n. Okay, for this. So what is the value of this? So this is equal to, as we did before, E of n times d head of n, because error is this. Okay, now this is equal to error times, E of n times d of n minus, I have error times d head of n. So what's d head of n? It's a linear combination of all of these. So let me write that as h of k prime x of n minus k prime, like this. Okay. So again, this will be, no surprises, equal to 0. All of these terms. Okay. The reason is expected value of E of n times xn minus k prime for all k prime. This is a summation over k prime. By orthogonality principle, for the optimal filter, it is equal to 0. And I'm working with the optimal filter, as you see. So optimal filter's error is orthogonal to the observation or input samples. Okay, so I'm left with this as before. So again, if I substitute d of n minus d hat of n over here, I get rd0 dn square minus k prime minus infinity to infinity h of k prime rx. So this is d hat of n, am I right? I'm multiplying this by d r, this is dx k prime. Okay, so dn is multiplying by d hat of n, dn times d hat of n, dn comes over here, so the expected value of this one is r dx of k prime. Okay, that is it. So this is, let's say, j minimum value for IIR non-causal filter. Okay, so I have such a relationship. Very good. So what else? I can, well, one issue. Since I have already expressed this in terms of its DTFT, so why not express this one in terms of its DTFT? So how can I do this? Well, maybe I should, before that, explain this a little bit. So since Rd of k is 1 over 2 pi minus pi to pi Sd e to the j omega k d omega. So this is the inverse DTFT relation, right? That is the inverse DTFT. So Rd0 is equal to, let me write it over here, there is 1 over 2 pi minus pi to pi Sd e to the j omega, okay, d omega. Okay, when k is equal to 0, I have that. So how about this one? Let me write d omega over here, not to forget this, minus, I would like to express this again in terms of its DTFT. Do you remember something like this? Well, maybe you can remember the following. X of n, y of n, minus infinity to infinity. Let me put a conjugate over here. Okay. This is equal to 1 over 2 pi minus pi to pi there's a conjugate on y. So what is this one called? Maybe you can remember. This is called famous Parseval's relation, or now we are much more experienced. This is nothing but the inner product between two infinite length vectors, isn't it? So this is the inner product. So you may always associate this inner product with the angle between two vectors and so on. So this is the inner product between their DTFTs. Of course, one of them is defined in a discrete domain, the other one is defined in a continuous domain. But what is interesting is, so from a linear algebra viewpoint, this one is an inner product between x and y, okay, and this one is an inner product between Fourier transform of x, in this notation, let's say, and Fourier transform of y, okay. And if you remember basic, vectors, this is the Hermitian, so this is the adjoint operator. Then if you properly define this, this is nothing but identity operation. Okay. So what's the meaning of this? So this is the inner product relation. This is the inner product of their Fourier transforms. Then This inner product can be also calculated like this, meaning that I move this linear operator as an adjoint operator on the other side, on the second argument. But Fourier transform's Hermitian is nothing but the inverse Fourier transform. Or think about this like a matrix if you wish. Then you have this identity mapping over here. So then this is nothing but xy. So in other words, this says, a famous well-known result, if we have an orthogonal transformation such as a Fourier transformation or unitary transformation, the angle between input arguments x and y and output arguments, their Fourier transforms or their transforms, if this is some other transform, they have the same angle or they have the same inner product. Okay? That is it. This is what we call Parseval's relation. This is very important, and you can get non-trivial equalities by processing this. So about this one, well, we can write this one as, let me then move this over here, minus p, not p, sorry, this is s dx e to the j omega d omega. There's a conjugate issue over here. If you carefully evaluate this, there's a conjugate over there and conjugate over here. But for the real valued processes, this is real. But you have to have this conjugate on the second argument essentially. Okay? So that is it. So let me have it like that. Okay? Or let me erase this because I have done it for the real valued processes. So the second argument is conjugated, okay, according to this. Since this is already a real sequence, conjugate does not do anything, but I have to take, its Fourier transform and take its conjugate. Okay, so I have such a result, s dx e to the j omega. Now, what should I do next? Let me have an example on this. Let me discuss the filtering application. Filtering application for IIR Non-Causal Wiener Filter. Okay. So what's filtering application? Well, my x of n is observation, a desired process plus noise. So d of n, obviously desired, v of n, this is noise, okay, and they're uncorrelated. Okay, that is it. So for this problem, let's try to construct this filter, calculate the error, etc. So what can I do? Now for this problem, only thing that I need to calculate is, Rx of k and Rdx of k. Am I right? And take its Fourier transforms over here and, do this kind of a calculation. Okay, so let me try to do this calculation. So what is Rx of k? Rd of k plus Rv of k, because they are uncorrelated. Of course, I am assuming this is almost like the end of our course, zero mean processes. I have such a case. We have done this several times before. How about Rdx of k? X of n times xn minus k. Multiply this by xn minus k from left. Xn minus k is present. Take the expected value. They are uncorrelated and zero mean, this term goes away. So this is d of n times xn minus k, Rd of k. Okay. Then take its dtft, almost done. Sx e to the j omega. This is St e to the j omega. Sv e to the j omega. This is Stx e to the j omega is equal to St. Am I right? That is it. So we are done. The ratio calculation and insertion of this filter over here. But let me write the name of this filter in order not to get confused. IIR non-causal. Okay? Well, that is it. So then for this application, so what is my conclusion? IIR non-causal filter frequency responses. So this is this. I have such a relation. Well, let's think about this. Let's have a few words on this. So, comments. Let me write my comments with this color. So, I want to discuss the properties of this filter. Number one. So clearly, this IIR non-causal e to the j omega is real valued. What do I mean by this? Well, the numerator is real value. Furthermore, this power spectral density is positive, non-negative, I should say. Okay, non-negative, and this is a real quantity. This is also the same. So the ratio is also a real valued number. So for every frequency, I have a real valued number like that. So what's the meaning of this? Well, this implies that h of n non-causal is an even sequence. Okay? This is an even sequence. It's just that. So we have such a case. So let's think about this. Why that is the case? Well, this is just a comment. Number two, I will discuss this later on. Number two, the optimal filter IIR non-causal processes each frequency, let's say omega x, let's say something like that, independent of other frequencies. So what's the meaning of this? Now if I focus on, let's say one of these frequencies, let's say omega x, a specific one, maybe pi over 4, something like this. So you see that to get the optimal filter's frequency response at pi over 4 or omega x, you need this information. So you need the information in the desired power spectral density at that frequency and the noise power spectral density again at that frequency and nothing else. So essentially the problem is decoupled, i.e. optimal filter design is a decoupled problem in frequency. So how can I explain these two comments? If our calculations are correct, so we have such results. So can I explain this one? So how can I give an explanation for this? Let me see my notes. I have written some brief notes. Well, on comment number 1. If you check lecture 37, we have discussed that the White-Sand stationary processes have no forward time or backward time, i.e. processes can be reversed without any change in their spectral, not spectral, but without any change in their, let's say, autocorrelation properties. Of course, this is spectral, but let me a little bit more clearer. Okay. So perhaps you will remember our discussion. So we were discussing linear predictors. So assume that you want to predict, let me put this over here, this quantity, this is the question mark, using these 3. Okay? Now you have a linear predictor, optimal predictor, estimating this one using these 3, let's say, observations. P is equal to 3. You want to predict this one as a linear combiner. Now you may have another problem. You may say that, okay, let me have a second drawing. This time, now you would like to use these 3 to predict this one, okay? So this is like backward prediction, because you are predicting, in a way, the history, backward prediction. So this is predicting what will be happening in the next sample. This will be predicting what will be happening in the future samples. So we interpret this, you know, this is a filter going towards like this. This is a filter going towards left like that. So this is going backward in time. So what is interesting in that, if I do this optimal predictors, you know, they give exactly the same prediction filter. So for example, if the nearest sample is multiplied by 0.6, also this one is multiplied by 0.6 for filtering. Okay, this is the weight. So if this is multiplied by 0.8, second nearest sample, this one is multiplied by 0.8, second nearest sample, and so on. So this is like the same prediction operation. So the weights of this filters are adjusted according to their, you know, distances from this sample that is to be predicted. Okay, in both cases. So no surprises that now if this process has no, let me erase this x then. We have already made use of this x. Okay. If this process has no backward time or forward time, then if you want to estimate, let's say this is x of n, so this is x of n. So if you have samples x of n minus 1, n plus 1, n plus 2, n minus 2, etc. over here, is it intuitive that you want to filter this x of n process, but the process has no forward or backward time? You can always flip this process and you get the same properties. So if you assign a weight alpha for this one in the processing, then you should also assign a same weight over here, because it can be the flipped process. So if this is weight assigned as beta, this is also beta. So this means that the optimal coefficients for the filtering operation, it has to be some kind of an even, this kind of even sequence. Because the one after and the one before, they are equivalently weighted because of the symmetry in time. Okay? So this is somewhat like an explanation of that from lecture 37. Okay? So this is our interpretation. So because the process can be flipped in time, linear combination weights, weighting the future samples or the past samples, they should be equal to each other. Okay? provided that they are equally distant from this d of n vector. And of course, this results in an impulse response like this. So this is like an even sequence. So this is 1, minus 1, minus 2, 1, 2. It goes like this. It's like an even sequence. Now comment number 2. So please remember, this is lecture 23B. So wide sense stationary processes are, this effect from that lecture, correlated by Fourier transform, are decorrelated by Fourier transform. Please remember that if I take, Fourier transform of x of n and compare the values of the spectrum at different frequencies, they turn out to be uncorrelated. Okay? This was lecture 23B. So then this tells us that if you have a random process, this omega x frequency and omega y frequency, they are uncorrelated. Meaning that for the sake of linear prediction or linear operation or linear combining, whatever your purpose is, those frequencies do not carry any information with respect to each other. If the frequency omega x and omega y, those samples of the spectrum at different frequencies, if they're uncorrelated, they don't carry any information about each other. Okay? So this is the reason that comment number 2, each frequency sample is just taken into account like that. Okay? So that is on comment number 2. So what's the meaning of this if we think about this? Actually, it's a very intuitive meaning also. So let's say that desired power spectral density is minus pi to pi. Let me sketch only this part. I'm just making this up. But this is something like this. So this is my S desired e to the j omega. So how about this noise power spectral density? Noise power spectral density is, let me say, it is more flat, but something like that. SV e to the j omega. Okay. Now at a frequency point, let me select this point. This, let's say, peak. Let's say this is omega x. So how do I interpret this result? So this says that the optimal filter at this frequency omega x, okay, is something like, as you see, well, this value, this is like the signal term, divided by, well, this is the noiseless power spectral density, okay, and this is their sum is, this is this length. So I have this length and this length. So this is nothing but the denominator is summation of these two lengths, because this is and that. So it is nothing but just the weighted average of, this is nothing but the weighted average of, this frequency sample according to these two weights. Okay? So at this frequency, for example, at omega x, if this is like 6, and let's say this is like 4, then I have the ratio of 0.6, isn't it? 6 over 10, 0.6. So at this frequency, then the optimal filter weighs this frequency component in the estimator. This is estimator's frequency response by 0.6. So because this filter is has the knowledge that 60% of the power is due to desired signal, 40% of the power at that frequency is due to noise. So there is this 60%, 40% ratio, and this is just implementing that. So this is implementing all of it for all frequencies, always the same for all frequencies. Okay. So a very intuitive interpretation. So if I look at a narrow band, let's say bandwidth over here, so it's always comparing, you know, at an individual frequency, these ratios. Okay. So that is it. Okay. So what should I do next? Let me also calculate for the specific example, this one. So let me comment 1, 2. I think I can erase this. Let's calculate this J-min IIR non-causal from this relation actually for the filtering application. So this is J-min IIR non-causal. So I want to implement this. 1 over 2 pi minus pi to pi. This is SD e to the j omega. Let me write this first. H IIR non-causal e to the j omega. S dx, there is a conjugate e to the j omega d omega. Okay. So for this, you know, filtering application, what do I have? So this is equal to SD of j omega for filtering application. Remember, Rdx of k was Rd of k. This was the first thing that we have written. Okay. Then let me do this operation a little bit. Let me use this part. 1 over 2 pi minus pi to pi. There is SDE to the j omega times 1 because of this. So this is also SDE to the j omega minus this filter, but this is equal to this one. This is also SDE to the j omega divided by SDE to the j omega plus SVE to the j omega d omega. Am I right? So I have written this filter for this one, and that is it. Now if I do this operation, so equate 1 over 2 pi minus pi to pi SDE to the j omega times SVE to the j omega divided by SD e to the j omega plus SVE to the j omega d omega. Am I right? Just move it over. There is a cancellation. There is SV on the numerator. I think that is it. So, but let's also note this one. This is also equal to this. So this is H IIR non-causal e to the j omega because it's the same expression. Okay. So I get this result then. One over 2 pi minus pi to pi H IIR non-causal optimal filter frequency response times power spectral density of the noise d omega. Okay. That is it. So this is the end of this discussion. So this is J-min IIR non-causal. So since I'm expressing this filter in the frequency domain, I'm also calculating the error using this frequency domain representation of the filter. Now there is a special case. If SV is white noise, okay, let me write that. If RV of k is sigma v square delta k, then its DTFT is, I have, let me write, SVE to the j omega. Okay, so this is equal to sigma v square times, that is it, sigma v square. Okay. So this is the white noise condition. Let me write white noise by this. So as we have said, white noise means the following. In the spectrum, all of these frequency components, let's say it's flat, and I have, let's say, sigma v square. So they're equally weighted over here. So all of the frequency components are present, but they're equally weighted. For example, this red one, it's not clearly white noise because some of the frequency components are, more powerful in the processing or in the generation of this noise process. Okay. Okay, so if this is the case, then J min IIR, this value, just insert it over here. I have sigma v square times, well, I get a very simple result. IIR non-causal. The reason is, if you include this thing in this integrand, then move it out of this integrand. It's present over here right now. So this is the area under the frequency response of Hj omega, which corresponds to the zeroth sample of this impulse response. Okay. So for white noise, we get an especially simple result, sigma v square H0. So let me see. Okay. So let me have a numerical example on this. Actually, this is one of the examples that we have previously studied. We continue with the same example, but this time we are implementing FIR Wiener filter. So let me check this. So x of n is d of n plus v of n, then rd of k is 0.8 to the power absolute k, and rv of k is, let me write sigma v square delta k, but in this numerical calculation we had previously also taken sigma v square is equal to 1. Okay, so previously we have calculated, maybe you can remember, a two-tap filter for this. Two-tap FIR Wiener filter. We have calculated one-tap FIR Wiener filter for the same one. So for the two-tap result, maybe you can remember from this earlier lecture, J minimum two-tap value was 0.4048. J minimum one-tap value, one-tap FIR filter, was 0.5. We had some earlier results like that, okay, from previous lectures. And this was a topic that we have discussed, SNR, maximum SNR filter, whether this MMSE minimizing filter is a maximum SNR filter or not. Okay, this was the same example. Now the goal is constructing this IIR non-causal filter. Construct IIR non-causal filter and compare its, let's say, MSE value with earlier examples, with earlier cases, let's say. Okay. So So let's go ahead. Actually, we are very well equipped for the solution. So what do I have? So here is my result. But let me write everything in terms of Z transforms. HIIR non-causal Z is equal to S dx of Z divided by Sx of Z. And just a few seconds ago, we have expressed this as St plus Sv of Z plus Sv of Z. So I have to do this kind of a calculation. Okay. So then, what about this? So S, let me write it over here. S power spectral density of the desired process. So how can I find this? This is the Z transform of 0.8 absolute K. Okay. So this is, let me see, this one I guess. Okay, so this is Z transform of alpha to the power absolute K. Okay. This is equal to 1 minus alpha square divided by 1 minus alpha Z inverse 1 minus alpha Z. Of course we can derive this, but you know, this is topic of something else. Let's assume that this is given, or we know this, and let's try to use this. Okay. So then let me write this. So this is, okay, Sv of Z. So this is just, you know, sigma V square. This is the Z transform of R V of K, and this is just sigma V square, which is equal to 1. Okay. So let's put this aside. So what do I have? So I have 1 over, what, this is not, sorry, this is not, you're making a mistake actually. This is St of C desired, St plus Sv. Okay. So what do I have? I have this ratio, 1 minus alpha square, 1 minus alpha Z inverse, 1 minus alpha Z, plus 1. And over here, alpha is 0.8. In order not to make mistakes in this calculation, I haven't included it. I have written it in terms of alpha. So I have such a case. Then let me process this a little bit. Maybe I can get a reasonable answer in reasonable time. So let me try to do this. Okay, over here. Okay, this denominator part. So this is 0.8, 0.64. Okay. 1 minus 0.64 is 0.36 divided by 1 minus 0.8 Z inverse, 1 minus 0.8 Z plus 1. Okay. Am I right? I get something like that. Now, I have to process this a little bit further. So, how about this? So I get 1 over here, and again 1 point 0.8 times 0.8, again 64, with plus minus 0.8 Z inverse minus 0.8 Z. Okay? I get something like that. Then this is equal to, this part is the same. I have 36. This is 28, I guess. Is it 30, 66, 28? So I get this 0.28 minus 0.8 Z inverse plus, is this okay, 0.8 C. I get something like that. Then let me see. Am I making a mistake at this point? Let me see, just a second. According to my results, this is equal to 1.6, 1 minus 0.5 Z inverse, 1 minus 0.5 C, 1 minus 0.8 C inverse, 1 minus 0.8 Z. I have something like that. So is this equal to this? I couldn't check this one. So this is 0.25. And there's a mistake somewhere. Let me see one more time. 1. Oh, okay, I should add those two. The 1.64, so this becomes 2. Very simple. So I have 2 over here, okay? So if I have 2 over there, then I think I can derive this right now. So then in the brackets of 2, I have 1 minus, because 1.64 plus this, I have 2. 1 minus 0.8 Z inverse, 0.8 Z, okay, I have something like that. Then for this one, now I should factorize this thing. So if I multiply by Z, okay. So this is equal to, if I multiply, there is a 2 over there, let me multiply by Z and Z inverse over here. So let me also multiply by minus sign. So I have 0.4 Z square minus Z plus 0.4. So what's going on? So this is just 1, okay? So this is just 1. I have a minus sign over here. So essentially if you multiply okay. If you multiply this part by Z, you get, sorry, if you multiply this part by minus C, you get this part by minus C. Okay. 0 point this, then you have this constant term over here, minus C over there. Then to compensate with this, I'm multiplying by minus C inverse at the outside of this bracket. Okay. So again, if I pull this term one more time, this part, this is 0.4, if I write this as z square minus 1 over 0 point, this is 2 over 5, 5 over 2, plus this is 1. Okay. So again 0.4 brackets. I have this and so on. So if you check this, now this is equal to hopefully z minus 1/2 times z minus 2. Okay. I think we are getting somewhere. So at the end, if I collect these terms, I have 0.8 z minus 1/2 z minus 2 divided by the same thing. This thing goes over here. Okay. Now if I how should I write this? Now I would like to collect all of these terms. Let me see. This is now let me multiply there is also z inverse over here. Okay, 0.8, there is a z inverse. Okay. Now let me process this part first. I have minus 0.8, 1 minus 1 over 2 z inverse. Okay. How about this? Let me pull this minus 2 out. 1 minus z inverse over 2. Then I have, with some difficulty, managed to get this result, I guess. Okay, so I get the result something like this: 1.6 times 1 minus 0.8 z inverse 1 minus 0.8 z, 1 minus 1/2 z inverse 1 minus 1/2 z. Okay. Is this correct? Hopefully, at this point, it is correct. Okay, so I have managed to express this part. Now, if I write this, then now, if I include it over here, then what do we have? We are almost done actually. This is 0.36, and there's cancellation of this. So at the end, I get this 0.3. I'm just writing it like this: 1 minus 1 over 4 in the factorized form. 1 minus 1 over 2 z inverse 1 minus 1 over 2z. Okay. Now if you divide this, what happens? So this is 0.8 z inverse 0.8 z. This cancels. So you are left with, on the denominator, 1.6 times this. So that is over here. And that 1 over 1.6 times this one is the numerator part. Okay. So why am I writing this numerator like that? Because I want to use this result. Okay. Now, from here, we are done. Then H, IIR, non-causal of N, is then inverse Z transform of H, IIR, non-causal Z. This. Now I want to use this, so So I get 0.3, 1 over 2 to the absolute k. So if I sketch this impulse response, so it's like 0.3 over here, 0.15. So indeed it's an even sequence, so am I right? So 1, minus 1, 2, minus 2. This is 3, minus 3. Okay, so this was the thing that we were expecting, because in the processing of this, a filter is combining, samples, isn't it? So to generate an estimate for the nth sample, it's processing current sample by 0.3 in this case. Then the next sample or previous sample by 0.15 because of this convolution, and the previous sample with the same weight. Because the processes are always reversible, why should they have a different weight, isn't it? Then second sample in the history by 0.1575, okay, by this number. Then second sample in the future of this sample, and sample is by the same weights, because processes are, as we have said, reversible. Okay, so we got this optimal filter. Now the question is, what is this? The minimum error for this one? Well, we had a result. Maybe we can derive that result, but so J minimum IIR non-causal is, so what was this? We have derived the result. It was like sigma v squared times h IIR non-causal 0. But remember that for white noise only. For white noise v of n. So this is equal to 0.3. Because, h0 is 0.3 and this is equal to 1. Okay. So is this correct? Well, let me see. I think I have an illustration of that also. Let me do that, and that will be our final, calculation for this case. So let's calculate J min IIR non-causal using time domain results and compare with over here sigma v square h0 IIR 0.3 value. So what is this J min IIR non-causal? So this is RD0 minus, well, this is h of k r dx of k. This is our general result. Okay. So what is RD0? This is alpha to the power k, which is 1. How about this one? This is this is for k. H of k is this thing. Well, let me put the 0.3 over here times 1 or 2 to the absolute k. What is Rdx of k? That is 0.8 to the absolute k. That is it. So I should evaluate this summation. So how can I evaluate this? Well, I can do the following. 1 minus 0.3. So I can write this zeroth term over here. Zeroth term is just 1. When k is equal to 0, I get 1. Minus k k minus infinity to infinity, but k is not equal to 0. 0 term is over here. I have, this is 0.4 to the absolute k. Okay? Am I right? 0.8 divided by this, I think, okay. But this is right now an even sequence, because this goes from minus infinity to minus 1, then 1 to infinity. This is the reason that I have separated this. So this part is equal to 2 times k is equal to 1 to infinity, 0 point this to the absolute k, but now I don't need absolutes because k is always positive right now. Okay, so how can I calculate this? This is 2 times 1 minus, this is just 1, and the first sample is 0.4, so I get this as 0.8 divided by 0.6. Okay, so this is 4 over 3, 1 minus 0.4, this is also 0.8, is this correct? This is plus. Okay, so this is 4 over 3, then 1 minus 0.3, 1 plus, is it 4 over 3? 4 over 3. 4 over 3. So this is 7 over 3. So this is 0.1, 0.7. I get 0.3 one more time. Okay. That is it. This is 0.1 times 7, 0.7. I get 0.3 one more time, and it matches this. Okay. So as you see, I can calculate using this general result or using this very specific result for IIR non-causal white noise case. Okay. Okay, so we will continue from this point on with more discussions. Let's stop for now.